Perhaps we've all experienced electrostatics at work when you shuffle your feet along the carpet and you touch the doorknob and you get a little spark. And that's our topic today is electrostatics. So one thing we'd like to be able to do is use the basic structure of an atom to explain how objects become electrically charged. We want to use that to explain conservation of charge. And we're going to introduce a new unit called a Coulomb. And we're going to use that to find the charge of an electron or proton. And then we're going to develop a law called Coulombs Law that will predict the force between any two charges. And then we want to look at how things can we're going to predict the charge that will occur when two insulators are physically rubbed together. And we're going to be able to predict what charge they will get based upon how well that insulator holds on to electrons. And that's called charging by friction. We're going to also look at induction, conduction, and polarization. So, basic structure of an atom, and I need to acknowledge that this is way oversimplified, a lot more complex than this, but it really is a sufficient model for understanding the basics of electricity. First of all, hopefully in middle school, you've learned about a little bit about the atom. You have the nucleus. Protons and neutrons are in the nucleus. The electrons are swarming around in orbits around the nucleus. And we'll stop that so you don't get distracted. But electrons have a negative charge, and they have a very, very, very tiny mass. And protons have a positive charge, and the mass of a proton, I believe, is about 8,000 times the mass of an electron. So protons are a lot more massive. A neutron has no charge, and it has a very, very similar mass as a proton, but it's not exactly the same. And I'm going to go off on a little tangent here just briefly, referring to conservation of charge. But you cannot create nor destroy net charge. If you're going to create a positive charge, you also have to create a negative charge as well. And so one thing that's interesting is if you take a proton, which has this much mass, and force it into another electron, combine those two things, the mass of a proton and the mass of an electron is almost the same as the mass of a neutron. It's not quite the same, and that's where Einstein's equation E equals mc squared comes to play. But if I combine a proton and a neutron, a negative charge and a positive charge, there's no net charge, and that's how you can create a neutron. And that's what happens when a star dies and gravity wins out and the star starts to collapse, and the gravitational force pulls the star so tight and so compact that the electrons are crushed into the nucleus, and the electrons and the protons combine to form neutrons, and that's a neutron star. We're not going to go into any more detail on that, but we are going to look more at conservation of charge. That if I had an atom here with 6 protons and 6 electrons, it is neutrally charged. There's no net charge, and this atom is the same. Those electrons are swirling around. But again, we're not going to create nor destroy a net charge. We can make this positively charged and this negatively charged by taking electrons from one to another. So now if this one had 6 positives and 4 negatives, there is a net positive 2 charge on this atom. And because this one gained 2 electrons, it has 8, where before it had 6. There is a net negative 2. So all charging occurs by either adding electrons to an atom, making it negative, or taking electrons away from an atom, making it positive. So all charge is done from moving electrons around. The protons are bound so tight in the nucleus, typical everyday things that we encounter, protons don't move. So we know that there is a repulsive force between two similar things like two electrons or between two protons. Electron here and electron here have the same charge, so they're going to be repelled. Protons and protons also have the same charge, and they're going to be repelled. We know that opposite charges will attract each other. There's a force pulling those two things together. But then the obvious question is, well, how much force is there? If there's a force, can we predict how much that force is? The real question here is what variables affect how much force there is, either pulling them together or pushing them apart. Before we answer that question, we need to define a certain quantity of charge. Now, we have talked about fundamental units. It's also called the MKS system. All distances we measure in physics are done in meters. All mass is measured in kilograms. All time should be measured in seconds. That's the MKS system. And up until now, those have been the only three units that we've used to measure everything. Velocity was meters divided by seconds. Acceleration was meters divided by seconds and divided by seconds again. And everything we looked at was those. We now have another fundamental unit called a Coulomb, and that is our fundamental unit of an amount of charge. Now, just like if we had a dozen eggs, the word dozen represents a specific amount, a score, 20 years, a ream, 500 sheets of paper. The simple idea here is that one word can represent a specific number of items. And if we had a whole heck of a boo-foo bunch, that's just being funny for a large amount of charge, we can talk about a Coulomb worth of charge. And one Coulomb, by definition, whether they be positive charges or negative charges, is 6.24 times 10 to the 18th charges. So that's 1,000, a million, a billion, a trillion, a quadrillion, 6.24 pentillion charges is how many electrons or how many protons you would have to do to get 1 Coulomb worth of charge. Now, if you took the reciprocal of this number, took 1 divided by this is how many charges make up a Coulomb, but if you took the reciprocal of that, you would get how many coulombs there are per charge. And that's 1.60 times 10 to the negative 19th coulombs. And that's what a single electron. Electron is negative. If we were referring to a proton, it would be an E, but a positive sign. They have the same charge, but opposite. So, which of the following charges are not possible? Well, that's just the charge of one proton. It had a positive charge. This has the same charge, but it's negative, so that's also possible. 10 to the negative 10 is 10 times smaller than that, and that would be 1/10 of a proton. And that's the one we can't do. You can't have 1/10 of a proton. This would be just 2 electrons, or 10. I think I meant to have that as 18 instead of a 19 there. But yeah, you can have 10 electrons. Coulombs Law is an equation that helps us that will allow us to predict how much force there is between two charges. And we can set up an apparatus here where we take these metal plates and insulate them, so whatever charges we put on those plates stay on those plates. And if this is negatively charged and that's negatively charged, they're going to put a force repelling each other. That plate is going to get pushed down into our scale, and it's enough force that we can actually read it with not too high of a tech scale. We can change the distance and see how that affects the force between those charges. Now, we developed what was called the inverse square law with light. And no surprise, if I had a piece of paper close to a light bulb, it's pretty bright, but the further and further and further away we get, the dimmer and dimmer it becomes, and the closer we get, the brighter it becomes, and it follows an inverse square law, where the light that was hitting that, when we go twice as the distance, it's covering now 4 times the area, so the intensity is 1/4 as much. And so the intensity, if this is 1, 2, 3, 4 times the distance, this dimension becomes 4 times as much. That dimension becomes 4 times as much. It is 16 times the area. So the light that was hitting one little area is now hitting is only falling on 1/16 that little piece there, and which is 1/4 squared. Same thing with gravity. Gravity diminishes with distance as an inverse square. And same thing with now electrostatic force. If I had a bunch of negative charges here and that charge got further and further and further away, the force would become less and less and less. All right, so the distance is an inverse square law. If I had a Coulomb here and a Coulomb there separated by some distance, there'd be a force of repulsion pushing those apart. But if I had twice the charge on one side as I did the other side, the force would become twice as much. If I did twice as much as I had over here and twice as much as I had over here, doubling it on each side would produce 4 times as much. 3 times here and 4 times here would be 12 times as much force. So it looks like the force is proportional to the product of how much charge there is. We use Q as an abbreviation for charge. C is used in lots of other things, so Q for charge. But if I say triple this here and 4 times this over here, something tripled and something quadrupled would result in a force 4 times as much. So the electrostatic force is inversely proportional to the square of the distance. Doubling the distance would be 1/4 the force. And it's directly proportional to the product of how much charge there is on either thing. So we put those two ideas together, combine them like this, and if this is proportional to all of that, we can say they are equal if we multiply by the right constant of proportionality. And that's called Coulomb's constant. We often just abbreviate that and say, hey, that's close enough to 9 times 10 to the 9th. And if you compare the electrostatic force to the gravitational force, you find that this is a very, very small number, the gravitational constant. So that means that the electrostatic force is super strong to the positive 9, and the gravitational force is super weak, times 10 to the negative 11. You need a whole bunch of mass to get an appreciable amount of force. Here, it doesn't take very much charge to get an appreciable amount of force. In fact, I should, I'll do this first. If I had a dome here with positive charge and a dome here with negative charge, well, those negative charges are going to be pulled with a huge amount of force. And as they jump, because they're attracted to here, as they jump through the air, they excite the air and cause the air to glow. One thing I need to say is that 1 Coulomb is actually a very, very large amount of force. So for that reason, we often use tiny fractions of coulombs, like a microcoulomb. But you could take this many coulombs and plug it into here and that here, and the distance multiplied by Coulomb's constant, and we could predict how much force there is. In this case, it'd be about 22 newtons. Now, looking on a smaller scale, if this is hydrogen and there's just a single proton in the nucleus, no neutron, and there's an electron orbiting around in a circle like this, well, it's just like a planet going around the sun. And we can calculate how fast that would need to go based upon how much force there is in the separation. So I won't go through this whole problem here, but we're going to solve for the velocity here. And if I take the mass multiplied by the acceleration, that would be how much centripetal acceleration we need, multiply by the radius, divide by the, multiply by the radius and then take the square root. We can solve for the velocity there. It's going pretty fast. All right, charging by friction. Let's see how we can get charges on atoms. This here is called the triboelectric series, and it's just for a few materials. But lots of materials, if you physically rub them together, materials from here up are likely to lose electrons, becoming positively charged. Items from here down are, if you physically rub them together, they're likely to gain electrons, becoming negatively charged. Things close to the middle only slightly will have an affinity toward gaining electrons, and things here on the ends are much more likely to gain, so on the extremes here. So if you have like a hard rubber sole here, and you have maybe wool carpet, and you physically rub those two things together, hard rubber is going to hold on to electrons better than the wool. So the hard rubber is going to become negatively charged. The wool will become positively charged. And that's how you can shock the nose of your little brother or sister. Or if cotton socks tumble in the dryer with a polyester shirt, cotton would tend to become positively charged, losing electrons. Polyester would tend to be able to grab electrons and become negatively charged. So one became positive, the other became negative, and they're attracted to each other. And that's why they stick together coming out of the laundry. Animal fur and hard rubber versus silk and glass. They're neutrally charged to begin with, but rubber will tend to hold on to electrons better than fur. So if you physically rub fur with rubber, the rubber is going to grab electrons off and make the rubber negatively charged, and the fur became positively charged. Silk holds on to electrons better than glass. So if we rub those two things together, the electrons are going to come onto the silk, becoming negatively charged, and the glass would become positively charged. If this kid slid down the slide here, this material and whatever the kid's wearing grabbed electrons, and the hair stood up because the charge that's on the hair is just trying to get away from each other. Be careful getting back into your car when you're filling up the tank, because when you touch the nozzle here, you can create a little spark because the pants on the upholstery of your chair made a charge on your body. These are called pith balls, and pith is just a fibrous plant material that's been coated in graphite. These actually look like they're styrofoam balls, but very similar. Remember that rubber became negative and glass became positive. If I touched the rubber rod to these pith balls, they would become negative. So this became negative. It gave electrons to it. If this touched that one, now that would also share those electrons, and they would both be negative, and they would push away from each other. If you now brought a positive rod near those things, they would be attracted. An electroscope is a really good tool for seeing if something has charge, and it's called a gold leaf electroscope. That's actual gold foil there, and we use gold because it's conductive, but it also can be very, very thin, lightweight, and malleable. So if this whole thing here became positively charged, like electrons were taken from it, the gold leaf here was positively charged, the plate behind there was also positively charged, and that positive charge is going to make that gold leaf move off to the side here, indicating that it had a charge. It doesn't tell what charge it has. It doesn't tell if it's negative or positive, just that there is a charge. So if I brought a rubber rod here that had become negatively charged, remember, it's not the positive charges that move. Those are protons. They're locked in the nucleus. It's the electrons that can move through this. So these electrons here are repelled by those. And as we bring this closer, these electrons are going to get pushed deeper. This is negative and that would make the gold leaf stand up. This was done without actually touching, so it's called induction. If this had physically touched, it would be called conduction. If I brought a positively charged glass rod there, it's not going to push the positive charges deeper. Again, those are protons locked in the nucleus. They don't move. But the electrons are free to move. So if I bring this positive charge near it, the electrons get attracted up to it, leaving it charged down here. All right. Now, if I bring this rod near it, and it's going to attract these electrons up toward the top, attracting them up here. While all those electrons are up there, I now go ahead and touch it. Those electrons don't want to be all packed together like that. If you give them a place to go, they will go. And when I take my finger away, it will stay charged. Conduction is where I actually take my rod here and touch. And when we touch, we'll usually see a spark. And these electrons are going to try to neutralize, trying to get an equal charge up here as it is down here. But since electrons left, it became positively charged. All right, so we could rub our feet on carpet here, and as long as we had different materials, we could build up a charge. If we put that carpet on a treadmill and put our foot on there and ran that treadmill, boy, we could build up a big charge and doing the work for us. And that's what a Van de Graaff generator does, except it uses 3 dissimilar materials: polyurethane, soft natural rubber, and then a hard, and then wool. So here's what happens. In the bottom down here is this roller, and this roller is covered in wool. And there's this belt that goes from the bottom roller down here to another roller up there. That roller is made out of urethane. So this belt goes all the way up like this. And there's this metal brush that is connected to the ground, so it can get electrons or deposit electrons from the ground. As the rubber belt rolls around the wool here, the wool is going to become positively charged. This natural rubber will become negatively charged. So it's going to pull electrons off of the wool and put them onto the belt. So the wool became positively charged. Now what happens is if the wool became positively charged and there's electrons in this metal comb here, those electrons are going to be attracted to the positive charged wool, and it's going to jump over toward them. But as it jumps over toward them, the belt gets in the way, and because it's spinning, it carries that charge up to here. And then let me finish explaining about the top here. The urethane here became negatively charged. So when that electron got up to the top here and hit all that negatively charged, it was repelled away, and it's going to jump over onto that brush there and be carried away to the rim of that dome. And it's just going to keep going round and around and around. It's going to keep depositing more and more and more charge up there. And if you use that Van de Graaff generator and put a whole bunch of negative charges on a pie pan that's out of the view of the camera here, right now this is there's no net force on there. We zeroed out the scale. But watch what happens as I bring that scale, bring that other pan close to it. It's going to get lighter and lighter and lighter with a negative there. Then that spark happened, and now it became heavier. It was negative at first, and then it went positive. So let's see if we can explain it visualizing electrons. We touched this thing to the Van de Graaff generator and put a whole bunch of electrons onto that. When we brought this thing near, we got a negative number, which means it was being lifted up. A positive number meaning it was pushed down. Well, why was it lifted up? Well, the electrons that are in this metal pan are free to move, and they're repelled deeper into the metal here, leaving positive charges behind. Well, these positive charges are attracted to these negative charges, and these negative charges are repelled by those negative charges. But the overall attraction wins out. These charges being attracted to here is a bigger force than those negative charges being repelled by these. And it's bigger because it's closer. if I got that close enough and actually let this pan touch here, then those charges are going to jump and try to neutralize. So it actually got close enough to actually conduct and bring some of those charges down here. Now that's overall negative, and this is overall negative. And so the net force here is going to be an repulsion. It's going to push this plate deeper, and that's why we got this little extra weight on there. Charging by polarization, sometimes the electrons aren't actually free to move around, but they can shift from one side of the atom to another. So if I brought a balloon here near it, the electrons here are going to be attracted, and what happens is the whole atom kind of reorients. And that's the same thing as the previous example, where these negative charges are attracted to these positive charges. These positive charges are repelled by those, but because these were just a little bit closer than those, there is a net attractive force, and the balloon would be held to the wall. Water is a polar molecule. So if this balloon became charged and we had a water molecule, 2 hydrogens and an oxygen, the hydrogens are positively charged, the oxygen is a net negative charge, and it's going to reorient like this. The positives are attracted to the negatives. The negative is repelled by the negatives, but these are closer to that. So there was a net attractive force. And just an example, my last example here, a bunch of negative charges are going to be put to this terminal. This is going to become positively charged, and that's just a ping pong ball painted in graphite. Once that ball touches there, it becomes negative. This terminal and the ball are both negative now, so it repels. And when that ball touches over here, the electrons go zinging away, and they both become positively charged, and they repel, and it just goes back and forth. And that is the foundation of just electrostatics.